So when we have two things, just like when we had the two dice from the last example, we can make a chart and we can look at what's on the one spinner, 1, 2, 3, 4, 5, what's on the other spinner, 1, 2, 3, 4, 5. These happen to be the same, but you see how I wrote 1, 2, 3, 4, 5 for spinner 1 and 1, 2, 3, 4, 5 for spinner 2.
We're tough.
And Keaton, were you here when we got the
Yeah, dude,
package
bro,
for
join us.
of the total probability that it's bigger? It's a big
No.
I wasn't here.
Wow. I bet.
Have you got this book?
I'm not.
So bring this.
He's not like us, bro. He's not brave. He's not
Week or
tough
so.
like us.
Okay,
Put what away?
we're on page 4.
Put what away, bro?
So then, on this spinner, if you got a 1 on spinner 2 and a 1 on spinner 1, does it make sense you get a 2? And if you got a 1 on spinner 1 and a 2 on spinner, then adding them up, you would get a 3. See if you can fill out the rest of the chart. I've got the first row there. There's some other numbers.
How do I do this?
Well, if you got a 1 on spinner 2 and a 3 on spinner 1, your total would add up to 4. So we're figuring out what the possible totals are for each of those ones. Try to fill in the rest of the chart. Okay, good. People are done. Awesome.
Yeah. Is there test from last week in power school?
Not yet.
Oh. Oh, what? Yeah, bro, this part's always the last.
How did you do? And then once the chart is there, then we can solve probability questions. If you spun both of those and added them up, what is the most likely thing to get? What happens the most? Look at your chart. The 6, right? So then we would say, which total is the most likely to occur? It is the 6. What is the probability of the 6? Well, in total in this box, there are 25 numbers. Because there's 5 one way, 5 the other. A quick way to do that is 5 times 5 and get the 25. How many of them are 6s? 1, 2, 3, 4, 5 of them are 6s. 5 out of the 25 are 6s. That reduces to 1 out of 5. The probability of getting a 6 is 1 out of 5. If you type 1 out of 5 into your calculator, you would get 0.2. If you change that to a percentage, you have a 20% chance of getting a 6. It's the most likely. Next question. Which is the least likely to occur?
3, 2,
10.
The 10 or the 2? Because they both only happen once. So we would say either the 2 or the 10 only happen once, so their probability is 1 out of 25. So when you're playing games like Monopoly, you now start to realize, oh, it's more likely I'm going to roll a 7 than other numbers. It's not very likely that I'm going to roll a 2. So if you want to roll a 2 to get to a certain spot, chances of that happening are not very good. You'd have to be really lucky in order for that to happen. All right. Next question. Lisa's ordering her lunch from the canteen. She has choices of whole wheat or 7 grain, lettuce or tomato, tuna or ham. And we can create what is called a tree diagram with her choices. And so the way a tree diagram works is there are what we call, it's called a tree diagram because as we go off, sometimes we say we branch off in different directions. So a diagram that has branches makes sense to call a tree because trees have branches. And then you have your first choice here, your second choice here, and your third choice here. So first she has to decide what kind of bread she's going to have. This looks like a sub. It's a sub date. And you can't, I don't know why you're not allowed to have lettuce and tomato. They're like, no. I mean, maybe things are expensive. You're like, you're only allowed one vegetable. You have to decide, is it gonna be lettuce or is it gonna be the tomato? Who's getting that whole debate? And then what meat you're gonna have. So each of the branches together, like this top branch represents getting whole wheat, lettuce, and tuna. Oh, I don't like how tuna starts with T and tomato starts with T. The second one here is whole wheat, lettuce, and ham. I'm going to use the third branch. I'm going to use a little t for tomato and a big T for tuna. You see how I'm listing those? I'm going along the branches. If I take a highlighter out here and just do a highlight, this goes this branch to whole wheat, to this branch to tomato, to this branch to tuna, makes whole wheat, tomato, tuna. I don't think I would order that one. That does not sound delicious to me for lunch. Go back one slide? Yeah. Here's the previous slide if you didn't quite finish it. So now, how many different sandwich combinations are there if we look at the end of the branches? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 of them. What is the probability that Lisa orders a ham and tomato sandwich on 7 grain? I'm going to highlight that one. I'm going to highlight that one, that branch, in green. So she's ordering 7 grain, tomato, ham. That's this branch right there. Do you see the probability of, whoa. What did, I had nice, wasn't it? Oh my goodness.
It's too nice.
It was there. That's nice, there we go. Does it make sense that the answer to that is there's 1 branch out of the 8?
Yeah.
So our chances of ordering that, or probability of ordering that, favorable over total 1 out of 8. So if we can count how many there are, then your chances of getting it right. Right? Like if you tell me randomly to stop on here, I took out 13 cards already because I was getting ready because there's 13 of you and we're gonna get in random groups. So 52 minus 13 is 39. So if we say stop at a certain card, my chances of getting it right are 1 out of 39 because I took some cards off. So if it was all of them there, it'd be 1 out of 52. Who wants to say stop?
It's only people said.
Okay, you ready? I'll start.
Yeah.
I'll filter through.
Wow.
You say stop when you're ready.
Alright.
Stop. Okay.
Broke up and
I'm gonna say can of clumps.
Oh yeah. We're not falling for this, bro.
Yeah.
We're not falling for it. We're not falling for this, bro.
You're not falling for it?
Yeah, we're not falling for this.
Probably full in
Do it again.
Yeah, do it again.
Do it again. I'll tell you when to stop.
Again.
If it happens twice, we'll believe it.
You're peeking. Twice in a row.
Alright, stop.
It can't be.
Okay,
Okay.
I'm gonna go
You actually stop.
5 of diamonds.
No,
We're not falling, bro.
I fall for it.
What?
Yo, are they all like sorted in order or something?
What?
Pull 3 flops there.
You said stop. I can't pull whatever I want. You're the one who's saying. You're the one
Bro,
who's saying
Capu,
stop.
say what you're gonna get before he says stop.
Yeah.
But then it won't work, right? Because it, like, right, like here. If you said stop here, it only works if it's the not missing. Right? So I can only guess. You can't say before, and then I have to guess after. But it's just, that was super lucky, right?
Can I mix around? Can I mix around?
How about like
I dare
we
you to
have the
mix
cards
them
and
around.
you say what it's
Yeah,
gonna
if
be.
I can
and then
mix
we'll flip it
around.
over.
Oh, that could work.
You have that.
You think I'm doing some sort of trick here?
Yeah, he is. We're not falling for this, bro.
Yeah.
We're like not.
That's
I
how you
don't-
won't say it.
I don't know any tricks.
Yes, you do.
Alright. Next one. Fill in this tree diagram to work out all the combinations. We got first coin, second coin, third coin. Can you fill that in? Okay. This is flipping a coin. Yeah, I'm gonna erase these for now.
Yeah.
Yes.
Porque tiene la misma combinación de TH, TH, TH.
Because we say on a coin, cabeza, head, H. And then the other side, I don't know why. Why do we call it tails?
I don't know.
Because it has like an animal usually.
Because if you have a face on one side and you turn around, you have a tail. I don't know. But we say the side without the face, we call tails.
Yeah.
Colas. And so H for heads, T for tails. Okay. Doesn't work good in Spanish because cabeza starts with C and cola starts with C. What do you say for the sides of the coin? Cara y cruz. Pero say y say otra vez. Okay.
JR, bro. We're JR.
What's the probability of getting all 3 heads? Do you see the total? How many possibilities are in total?
Yes, 1 and 8.
There's 8. So now the probability of getting 3 heads would be 1 and 8. 2 heads and 1 tail. I'm going to highlight that one in yellow. Can you see that I could get 2 heads and 1 tail on that branch? That branch can be represented by heads, heads, tails. I could get also, take out my highlighter again, I could also get 2, if I do this branch, right? That branch is heads, tails, heads. That still gives me 2 heads. Is there any other way to get 2 heads?
How's the possibility 3 of 8?
Well, I've got 2. Is there? There must be another one somewhere. Can you see it? Take out my highlighter.
Oh,
HDMI.
Tail, head, head. There it is. Those are the 3 branches that have 2 heads and 1 tail. So your chances are 3 out of 8 of getting 2 heads and 1 tail. 2 tails and 1 head. Can you see 3 of those ones? Here's 2 tails, 1 head. Here's 2 tails, 1 head. And here's 2 tails, 1 head. Yes. 3 out of 8. But sometimes it's nice to list them all. So if you, after doing your tree diagram, you can list what these are. This is HTT. This is THT. This one's TTH. And this is TTT.
Teacher.
Okay. So now let's see if you can figure out this. This is a little bit different. They say, what is the probability of getting 1 head first, then 2 tails? So you have to do this. How many ways can you get 2 tails after that? How many branches? Only the one way. So that probability is going to be 1 out of 8. Probability of 3 tails, only one way, 1 out of 8. At least 2 tails. I'm going to take out my purple marker and talk about at least. What does at least mean? You could have 2, or you could have more. You could have 3. So does it make sense that I circle this one? I'd circle this one has 2 tails, this one has 2 tails. No. Yes. No. 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 How many did I circle?
3, 4.
4. 4 out of the 8, which reduces to 1/2. Okay, something to fill in your notes. This space, complementary events. So sometimes in your notes, there are spaces that we're going to follow along and fill in. And that one is complementary events. That's when you have 2 outcomes where one occurs if and only the other one doesn't. Okay? So sometimes we talk about things that it's either one or the other. Like, it's either daytime or nighttime. You can't have both at the same time. The sun can't be up and the sun away at the same time.
Well, wait, generally, like, can it be away and up at the same time if you're like 2 sides of the world?
What about a solar eclipse? Is
It's
this?
there, but like it's gone.
Yeah. Okay. We can. I mean, there's always like, if you're standing outside, can you be rained on and not rained on at the same time?
Yeah. Yeah.
Umbrella.
No. But then you're not rained on.
Yeah.
You're not getting. Then you're not rained on. Can you be both at the same time? I don't think you can.
Yeah, you just stick your leg out and have the umbrella.
But then you're getting rained on.
Yeah, and
If you stick your leg out, you're getting rained on.
and you're also not getting rained on. Just like
No, you're still getting rained on.
your
So,
leg is getting
We
rained
talk about this, like, can I flip a coin once and get heads and tails at the same time?
No.
No, I get one or the other.
Wait, what if it
Unless
what if
it
it like that?
lands
What if
on
it
the
lands on its
side.
Unless
side?
it lands, I don't think I've ever seen it land on its side. But I guess we could ask AI to do that for us. Okay. So if you have complementary events, then adding those 2 probabilities of one happening and the other one not happening. So we use this little, I don't know if you notice in the notes here, this little dash, that means not A. The probability of A plus the probability of not A is always equal to 1. Okay? What is the probability I roll a 6 or not a 6? If you roll a 6 or not a 6, you win. 4, I win. It's always going to be 100% when you add up the probability of one thing plus the probability of the opposite of it. It's always going to be 100%. Right? on a test. You can pass or you can fail. What are the chances you pass or fail? 100%. You're gonna do one of those two things. You can't do both of them at the same time. Sometimes you can change your failing mark to a passing mark later, but at the same time, when you get it back, you've either passed or you failed. You won't be doing both at once. So we can use this strategy to figure something out. If the probability that it's gonna snow tomorrow is 40%, this isn't true. I know we've had a lot of trauma this spring with it being so cold. It is not gonna snow tomorrow. But if they told you the probability of it snowing tomorrow is 40%, and then someone said, what's the probability of it not snowing? That would be 60%, because it's whatever it is minus 1. So I can either change it to decimals and do 1 minus 0.4, or I'll do it in green here. You could have done 100% as certainty minus 40%. That leaves you with 60%.
Yeah.
Oh, I went too fast. I'll go back. Yeah.
Yeah.
But you see probabilities all the time. Weather has probabilities all the time. If I open up my weather app, it's going to tell me one day next week there's percentage of rain and it's 30% chance. So then I'd be like, okay, I don't need it rain. It's probably not going to rain, but it might. Okay? You see percentages on your phone. What does it mean when you look in the top right hand corner of your phone and there's a picture of your battery and it says 22%? What should you start thinking about doing soon? Charging it.
No.
Because it's got a certain amount of time, certain amount of percentage left. They should have that above teachers, how much energy we have. Right? I have a little sign up here. 3%. And students? What percentage would it be?
They are.
60%. Yes.
How much cards are there in a deck?
There's 52 cards in a deck, right?
Is that with, without?
Without the jokers. You add the two jokers, there'd be 54. Yeah.
Yeah. Y esto lo va a dividir en tres siguientes, porque es como muy largo.
Where we're gonna have a quiz and a test
Okay.
on this unit because it's very big. Okay, here we go. Ready? Experimental probability. Add that into the box.
We're gonna make these boxes bigger.
You just have to write smaller. And then there's the formula there. So experimental probability is an estimate of what will happen based on an experiment. You're collecting data from an experiment. I have a story for you about this. Okay? Because some things we know. We know flipping a coin is 50%. But a professor at the university, I do not know why they wanted to do this, but they wanted to take something that had two possibilities. And here's something that has two possibilities. I've got a tack. I've got a tack. If I drop it, it either lands like this, where you don't want to sit on. I don't think you'd want to sit on it either way. Or it can land like that, without the point. But what's different about a tack compared to a coin is perfectly fair, 50-50. This isn't.
Yeah.
So what are the chances if I'm gonna drop it on the floor and make sure I pick it up because I don't want to step on it later. Oh, it's not in the sharp point up. But what are the chances of that? Is it 1 and 2? Or does 1 happen more often? If we do it 10 times, okay, here's first time. We'll do it 10 times. It's on its side. Second time. Point it up. Third time. On its side. Fourth time. Point it up. Fifth time. Point it up. Sixth time. On its side. Seventh time. On its side. Eighth time. Point it up. Ninth time. Point it up. 10th time on its side.
So
It happened to be perfectly 5 and 5. So that might make us think it should be 50-50. But is it guaranteed that it's 50-50?
No.
Okay, so this is a true story. Professor at the university was studying this and got money to study this to hire a student. And the student's job was to flip tacks all day and write down what happened.
okay.
How boring a job would that be?
I don't know, maybe that's basically 300.
I think the first, like, this, and if you have this job for a week and all you do is flip tacks, what do you think you think about when you go to sleep that night?
Tax.
Tax. I think the student actually went a little crazy as a result.
Like, if you're not allowed to, like,
But you have to, when you don't know the probability, the best way to find out what the theoretical probability would be to do a ton of experiments. So in that total, we did 10 trials, and we wanted to find the probability that the sharp point was up. We got 5 out of 10. So we're estimating 50%. The more experiments you do, the closer you should get to experimental probability. So we're going to do some examples here. Here's the first one. A survey was conducted to determine students' favorite brands of sneakers.
Mr. JR, what about example 10
Did we miss 10?
from like last time? Yeah. The 10th one.
Oh, maybe I just, there, this one.
Yes.
I don't know why I just missed it. I'll let you write those down. They're not too hard, right? There's 52 cards in a deck. 13 of them are hearts. So you would have to know a little bit about a deck of cards to figure these out. Which is 1 out of 4. But then someone could say, well, what are the chances of not picking a heart? Well, if it's 1 out of 4 of getting a heart, it'll be 3 out of 4 for not getting the heart. Because you could get a club, a spade, or a diamond.
What's the chances of me getting the age?
Okay, before we get into our groups, I'll see if I can do another trick for you guys. Okay.
Now this year, no problem.
Okay.
Okay, no problem.
Everybody ready on these ones? Okay. So what's the probability of a student's favorite sneaker being brand D? Well, if we add these all up, they all add up to 90. And do you see that 26 picked D? So we get 26 out of 90, which reduces to 13 out of 45. Pick D. Statistics and probability like this is really important because they use it in marketing all the time. They try to figure out what are you going to like. And if you like something more than something else, they'll make more of that one because then they can sell more of that one. So statistics and probability are very important that way.
like, like, the lowest number.
Yeah, so we had 26 out of 90 and we wanted to reduce that to the lowest number. I noticed that I could cut both of them in half, so I divided that one by 2 and I divided that one by 2 to get it to the lowest one possible. All right, we're gonna get to the bottom of page 7, and then we're going to work on some of these examples. So, suppose you I'll hide the answers temporarily for you here. Suppose you toss a coin 20 times, and you got heads 8 times. Okay? What is the experimental probability? You know the theoretical probability is 1/2. But according to this experiment, the experiment here says 8 out of 20 times is how much you get heads. That would be the experimental probability. What is the theoretical probability? 1/2. Here's a true story. People have a misunderstanding. Let's say I flip this coin and I got heads 8 times in a row. Now I'm going to flip it one more time. Is my chances of heads less than 50% now because I just got it 8 times in a row? Is it better than 50% because obviously I had it 8 times in a row? Chances are it's going to happen again. Is it less than 50 or more than 50? It's still exactly 50 from before. It doesn't matter how many times what happened before. It's always a 50% chance.
But now, what are the chances that you get it
I got
8
you.
times in a row?
Hmm?
What are the chances that you get that many times in a row?
That's a good question. What are the chances of getting 8 heads in a row? 1 in 256. Not very likely. So, if you start flipping coins and you say, I'm going to flip coins until I get 8 in a row. Oh, start again. Oh, start again.
Just use tens.
Oh, I got a head. 1. No, start again. I got a head. Here we go. I got another head.
SGR, una pregunta, ¿y cómo hace girar la SGR?
This is, but just wait.
0 points.
I did it 4 times. Theoretical probability says I probably would have to do it 256 times before it happened once. Not guaranteed that it will happen once.
SGR, ¿cómo hace para lanzar la moneda?
I got like this, like this.
Sí, pues, para mí es imposible.
Simple, simple. Okay. Oh, this one I don't like.
Lo que ustedes.
The theoretical probability is always the same. So just like tossing that coin, it's always 50%. But experimental probability is chance. And you have all the possibilities.
Oops.
The more trials you carry out, the more times you toss the coin, the closer the experimental probability should become the theoretical probability. So if I toss the coin 1,000,000 times, it should be about 50-50. But the chances of it being exactly 50%, there's mathematics to do this. I used to teach our grade 12 class that would have to do this. They'd say, you toss the coin 10 times. What are the chances of getting exactly 5 heads? It's not 50%. It's quite a bit less.
Pause.
But you can figure that out.
Oh yeah.
But it's a misconception. We could play that game. I could say I could toss it. I could even set up the money so you might be tempted to play it. I'm gonna toss this 10 times. If I get exactly 5 heads, I'll give you $40. But if I don't get exactly 5 heads, you've got to give me $10. Should you play?
Now, is it the same coin or can you just
Same
put like
coin.
10 coins all at the same
I
time?
could do all 10 at the same time. I don't know if I have 10.
Or you can do
1,
five.
2. Yeah, that'd be the way to do it.
Pencil dropped out my hand.
3, 4, 5, 6. Oh, I do. 7, 8, 9,
My pencil not.
10. Right?
Why is it
So we could shake them
I
up.
have it like barely hanging off.
We could put it down.
Yeah.
You can decide should you have played.
Yes.
And this is where, like, this is a real situation. I can figure out the mathematics that I can set the prices so I win more money than I lose. Would you play? Exactly 5, you get $40. And not exactly 5 heads, you have to pay me 10. Would you play?
Do a bit more.
Okay.
I'm playing.
You're playing? Okay, I got 1, 2, 3. I got 4 heads, 6 tails. You owe me $10. Okay, wanna play again? Wanna see if you can make it?
Yep. That was so close.
Paying the money, man.
This time I got 1, 2, 3, 4 again. You owe me $10 again.
Yeah. Está
Do you want?
truqueado.
Do you want to switch? Do you want to go with 4?
Yeah.
Go up 3.
You did what? Or how many heads do you think?
3 would be.
You get $40 if you do 6 heads.
No, I guess 5.
5 heads.
I'll let him do this.
1, 2, 3, 4, 5, 6. I'm already up $30.
Why is there mold on it?
There's copper. I don't know. They're like pennies are old now, right?
You're
don't make
actually gonna smell really bad.
And it was.
Ew! Oh my god, I hate that smell.
Okay.
Did you know that one penny actually costs 2 pennies?
That's disgusting.
Speaking, I can sell that much pennies.
So do that way.
Oh, did we miss example?
You got a couple of yellow bag.
After you.
Brandon,
there we go.
serious.
This is our last example, guys, and then we're gonna do some questions together.
This is math
Yo,
class,
I think
not
that
just.
is so.
Hey,
Yo, he dropped
Brandon.
the pencil. Sorry.
no,
Brandon.
thank you, guys. Here's our last question.
Math. A little fast. Brandon's my pencil.
Bro, that was very well. Very well.
Okay. Dale conducted a survey of students in his class to observe the eye distribution of eye color. 12 blue, 58 brown, 2 green, 8 hazel. Does anyone in this class have green eyes?
I don't know.
Great.
In the sun.
So I'm bad at this.
Oh,
No?
The sun hit your face at just
I
right
don't
angle.
know. I forgot what it
Does
was.
it count if-
The mixture is the hazel.
Oh, I'm going up.
The blue green mixture, blue green brown mixture is called hazel.
Yeah, Mr.
No, I just have the mixture.
Yeah. Mr.
Yeah.
Daniel tiene los ojos verdes.
Why don't you go with that colors?
Okay. So here's the first question. Find the experimental probability for each eye color. If you added them up, they all add up to 80 total people that were asked.
Yep.
So when we look at the blue, 12 out of 80, which is reduces to 3 out of 10, 3 out of 20. The brown, 58 out of 80, reduces to 29 out of 40. The green, 2 out of 80, reduces to 1 out of 40. And finally, the hazel, 8 out of 80, which reduces to 1 out of 10. So based on the survey, what is the experimental probability that a student in Dale's class has blue or green eyes? How many people have blue or green total? right? Blue is 12, green is 2,
14.
right? 14 out of the 80 would be the probability, which reduces to 7 out of 40. Next question. Based on the survey, what is the experimental probability that a student in Dale's class does not have green or hazel eyes? Does not have green or hazel. So green or hazel was how many people? 10. Right? Green or hazel was 10. Not green and not hazel would be the other 70 people. And the last question has a couple parts here.
Yeah. Y nos dará tiempo para copiarlo todo.
If the distribution of eye color in Dale's grade is similar to the distribution in his classes, and there's 360 people in his grade, how many do you think would have brown eyes? How many do you think would have blue eyes? So the probability, so if we look at the brown eyes one first, brown eyes was 58 out of 80, 29 out of 40. We could type that into our calculator and get a percentage. In fact, I'll do that right now. I type into my calculator 58 divided by 80. That is 72.5% of the class. So if I do 72.5% of 360, this is like our percentages unit, a percentage of something you multiply, you would expect 261 of the students to have brown eyes. So again, this is percentage of 360. I have the percentage here as the fraction. And whenever we do percentage of something, we multiply. That is a bad looking arrow. So blue eyes, what is the percentage of blue eyes? 3 out of 20 times 360. 54 people would have blue eyes. Not green eyes. Green eyes was 1 out of 40. Not green would be 39 out of 40 or 78 out of 80. You would expect 351 of them to have not green eyes.